All right, everyone. How are we doing today? Yeah, I need more weekend too, but here we are. So, there was some chatter about this before class got started here, and I want to address it so that everyone kind of has the shape of this in their mind. So, if you're worried about it, you can kind of uh, have extra mental time to deal with it. We're finally going to have an exam next week. It's of course, in the syllabus. And the way that that's going to work out is that this is the last week that we're going to be covering new material. It may be the case that we have a little bit of spillover into the early part of next week if we don't quite get through everything we need to get through this week. But um, what we'll do is cover new stuff this week, and then next week, in whatever time we have on Monday and Tuesday, will be review days for us to put things in order. I will try to take a little bit of time before the weekend on Friday to kind of clue you in onto the major things so that you have some opportunity to start working on that before we hit the review, the dedicated review days. And then we will have an in-class exam on Friday of next week to have things capped off. Okay. Um, just so you all know, and this is something that uh, I will decide as I'm for sure framing the test in my mind and putting everything together, is that for this class, because we only have a 50-minute period in here, what I will probably do is give you a set of take-home questions to go along with the exam. That would be structured in the same way as our weekly quizzes. Okay, so basically what it would be is maybe 3 or 4 questions that I think are things that we should be examined over, but aren't good for in-class uh, exam type stuff. Okay, if there was a question where I would ask you to use some kind of technology, there's some surface that I want you to plot, which wouldn't be much more complicated than just typing in the formula into one of the websites that we've used or something. Or some other a little bit more computationally intense problem, or something where I want you to have time to plug in the numbers and get a valid decimal approximation, that sort of thing. Okay. Expect that to replace the quiz for next week. And then the other in-class activity, of course, we'll have is just the regular exam, and that will be some appropriate number of questions, 4 to 6 things that'll be for you to handwrite out and do that. Okay. So let's jump in here. Section 14.6. Okay. So for directional derivatives, we've already actually discussed 2 very specific directional derivatives. Those are, of course, sorry, getting in a hurry. I don't want to write why not. Okay, these are the first partials with respect to x and y. Okay. So as we've discussed, if we have our coordinate plane here, and we have some surface that lies on our coordinate plane, if I'm differentiating at some point x naught, y naught, the way that this works is if I'm taking the derivative with respect to the x direction, I come up with a cutting plane here that slices through, that's parallel to the yz plane. And then what that does is it draws a curve on our surface here. And then the value of the derivative is the slope of that tangent line. Okay? That's what this operator does. Okay? It measures the slope of the tangent line after I cut through on that plane. Likewise, if I cut through on this plane, we get a different curve, and we get the tangent line, and that's what that looks like. Okay, so those are the pictures for our first partials and the canonical directions for x and y. What there isn't, however, is any rule that says that I can't instead choose this plane. We would get a different curve. We would want to know what the tangent line is. Okay, we need some way in general to deal with that. Okay. So there's some pictures of this in your textbook. And the notation that your book uses for this looks like this. Okay, so if we pick some other direction u, okay, the directional derivative in the u direction looks like the limit as h approaches 0 of f of x naught plus h times a, y naught plus h times b minus f of x naught, y naught, all over h. Okay, with u being a unit vector. Okay, so this is the definition of a directional derivative in a general in any direction. Okay. All right, and then I know I mentioned this before, but I just want to remind everybody. I teach linear algebra, and I've done linear algebra, and I'm just used to writing the double bar when we're talking about norms of vectors. Okay, it's the same. The book uses the single magnitude bar a lot to talk about the lengths of vectors, but in basically every other class you'll encounter this. People will write it with the double magnitude bars. So the reason again for this is that absolute value means length in some sense for numbers that we're familiar with, real numbers, complex numbers, and vectors. But the idea of a norm can be extended to matrices and operators. And so once you get to linear algebra, the more natural extension of ideas touches on that matrix and operators idea, which is why people transition to using the norm way of writing it. Okay. Something else to point out here is that the directional derivative has the requirement that the norm of our direction vector be 1, just for simplicity's sake, right? And both of these fall under the category of directional derivatives. They satisfy this definition because my direction vector here is 1, 0, and my direction vector here is 0, 1. Those are both unit vectors. Okay, so these are just special cases of the general formula for directional derivative. Because I get A is 0, or sorry, B is 0 in the first one, A is 0 in the second one, and then otherwise the formulas match up. Okay. Now, one of the very, very neat things about putting all this together is we have an extremely useful theorem for the computation of directional derivatives, which will save us a bunch of time. And that, thankfully, is that this is true. If we take the partial derivatives with respect to our canonical directions, x and y, we can get the value of the directional derivative by multiplying f partial x by a and f partial y by b. And does anyone have any guess as to why this is true? Vector projections. You take in vector form the partial derivative of f partial x and f partial y, and you project it onto a unit vector. Okay, so that's why this formula is true. I don't know if it's coming through on the microphone for those of you out there on the internet, but there's a video playing very loudly in some room that's close to us, and there's some chiming, and it's the kind of chiming that starts to make you wonder if you're gonna crack. Anyway, I don't know why they play those documentary things so loud. Yeah, because like yeah. Anywho, because that's one of the things that I had to adjust to is I don't know. I've been talking in classrooms for a while, and I've just gotten used to using more or less my normal speaking voice, but just projecting. You know, like you can get distance without power, and the acoustics of these rooms are for the most part good. You don't have to play the video super loud when you do need to do that. So yeah, no, that was going on over there too. But yeah, because I'm over here scribbling on plastic stuff that doesn't make noise. Yes. Don't want to know. I don't know if that's glass or not. It's very interesting. By the way, if you've never used one of these tablet things, so the ones that have screens are actually worse to write on than the ones that don't have screens, because like not that this one's difficult to use at all, but you have kind of a slippery like rubber stylus thing, and then it writes on the screen and it's okay. But I have another one from this brand that's just the actual tablet, So you just write on it, and then you would have another screen where you're reading what you're doing. If we were doing remote instruction, I'd be using that in my home office. But it actually is textured, so there's a much better like feel of using the stylus on the device as opposed to this thing where it's just like, if part of the reason why my writing gets sloppy is I try to write faster and it makes the pen slip. Anyway. Okay. Dun, 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 dun. I'm sorry, what? Oh no, I'm sorry. The live reporting on whatever's going on in the other classroom now involves a barbershop quartet. Okay, so that's so weird. Okay, okay. So let's talk about the theory, and then we'll go back and do some computations and stuff. I want to make sure that everyone's kind of following along with what it is we're doing. There are, as you would probably guess, some extremely important directional derivatives. We've already talked about two of those directional derivatives, being the partials in the x and y direction. If we have functions of higher dimensions, we of course will also have the partials with respect to any of the other directions for the independent variables that we have for the problem, right? All important directional derivatives. And then there is another additional directional derivative that is extremely important to us. And that is known as the gradient vector. Okay? So the gradient vector is connected to this expression here. Okay? We have this new vector that I have made, which is a vector composed of the first partials of our function, and then I've taken the dot product of it with our unit vector. Okay? One of the ways that we could rewrite this expression involves what will become for us extremely common notation for the gradient, which is this. Okay, we have this upside down triangle symbol, and that symbol is the one that we will use for the gradient. We take the dot product of that with our function u. Okay? This, of course, means that the gradient is defined in the following way. F, of course, needs to be a differentiable function. But if it is, we can say that it's equal to this, or we can write it in partial derivative form with unit vectors. Okay? And of course, if we have more independent variables, then we just add more terms, right? Okay. I think I mentioned last week that the funny looking D sometimes is called del. Okay. This thing is also sometimes called del. Yeah. Is it? Sorry, it's Nambla. Also this. If you use something called LaTeX, this is the word that you have to type in order to get that upside down triangle symbol. Anyway. Oh, Nambla. I can't remember if the M goes in there or not, but anyway, it's not important. If you use LaTeX, then you'll learn. All right. So, uh, this symbol is going to be something that shows up fairly often now. Okay. There is an important way to think about how this works, and it is in operator form. Okay. Because when we use this symbol in the future, we're going to append additional dots and crosses to it, and it's going to mean different things. And it is much more natural to think about how what we will eventually call the divergence and the curl work with this thing if we think about this upside down triangle as meaning the vector that is composed of taking the first partial and second partial of whatever this gets set next to. Okay, so when I write gradient f, what I'm saying is apply in order those two operations to f. Okay, this statement mathematically isn't super obvious what it means because there's no operation symbol here, but the operation is implied to mean to do this. Is it a horror movie now? What's going on? Yeah. Okay. Man, I don't know what's going on. Well, I mean, I guess depending on how you feel about things, this might be a horror story too. Okay. So, we're going to be doing a lot with gradients. This is the basic idea here. And for the immediate future, other than just computing gradients, which is going to be something that we'll see in applications, the directional derivatives can also be computed by using the gradient and just multiplying it by, or using the dot product with the appropriate unit vector. Okay, so let us do an example. Am I going to have enough room for this? We'll go to the next page. All right. So what we want to do here is find the directional derivative of the function f of xy is equal to x squared y cubed minus 4y at the point 2, -1. And we want our direction to be 2i plus 5j. Okay. So we've got some things to do. We need the gradient of our function. We need to compute the gradient of our function at this point, of course. And then we also need to, in order to be able to use the convenient formula for computing the directional derivative, make v a unit vector. Right? We have to make sure that it's a unit vector in order for us to be able to use the du formula. Doesn't really matter in what order we do these things, so let's start with v. We have this. If we want to make it a unit vector, We divide by its length. You can write that maybe if it makes the notation shorter. And so what we get is 2 over the square root of 29, 5 over the square root of 29. All right. And for the gradient, we just make a vector out of the first partials for our function. We take the derivative of f with respect to x. And we take the derivative of f with respect to y. Okay. You could probably have skipped that particular step of writing. I'm just being as explicit as possible here. We differentiate with respect to x here. We get 2xy cubed times I plus here we're going to get 3x squared y squared minus 4j. Now we evaluate at the point in question, 2, -1. 2 times 2 is 4, times -1 cubed is -4. That should be squared, you're right, thank you. I think I said it and didn't write it. Anyway. So yeah, fix that. I made a copy mistake there. Okay. Evaluating f partial x at 2, -1 gives us -4. And then we need to evaluate the other expression at 2, -1. We get 3 times 2 squared, so that's 12, times -1 squared, which is 12, minus 4 is 8. Okay. And now what we can do is compute our directional derivative at the point by taking our result for the gradient at 2, -1 and taking its dot product with our unit vector. Like so. Okay. So what we're going to get here is -4 times 2 to give us -8 plus 8 times 5, which is 40. So that's going to give us 32 in the numerator. And then the denominator, we're going to have the square root of 29. Okay, so that is the value of our directional derivative in this direction. Seems fine, right? Okay. So, the book makes mention at this point that if we were to talk about a function of three variables, it works the way that we want it to. Okay, you just write down more stuff and the formula stays the same. Okay. So there are examples of this that will come up in the homework for you to take a look at. I'm not going to say a whole lot about this because it's just a more mechanically tedious version of the problem that we just did. Okay, there's just more stuff to write down. What I will say, because this is going to end up being the much more common version of this that we see, I shouldn't write it like that. As we move forward, there are going to be some things that we talk about involving the gradient notation, okay, and in particular, this gradient symbol that I mentioned in its operator form of previously, okay. When we talk about gradients, most of the time we're actually going to want to be dealing with functions of three variables, okay, or at minimum, a implicit function of three variables where we might think of it as a surface, but z is equal to f of xy, and we might just have a parameterization for z, and we would differentiate with respect to z to make it look like this anyway. Okay? We're going to see a lot of this. And we're also going to see this version where the idea is you're supposed to take, again, an operator form, this. Okay? Let's just make a vector with the first partials in order of the function. Okay? Have any questions about that? Seems fine. Okay. Now, the next step is the real calculus. Okay. One of the things that we care about in calculus is being able to determine the maximum and minimum of things, right? It was one of the primary focuses of us all the way back in Calc 1 was we have this thing, the derivative, and this derivative thing tells us about rates of change. But with the ability to study rates of change, we became very interested in figuring out, can I analytically determine the value of x where this function bottoms out, okay? Or where this function tops out. Or if neither of those things happen, but something else important happens, right? We want to do the same thing here, except I have a more complicated setup. We have some surface, okay? And if I pick some point, I want to know in what direction do I have to travel to get the biggest derivative, the biggest value for the directional derivative. Now, what does the value of the directional derivative correspond to here? There is a tangent plane, okay? It's harder for me to draw a tangent plane that moves around, but you can think about that, okay? So imagine, well, okay, sorry, I'm thinking about the tangent plane thing. The, the tangent plane is a nice idea, but it already has something baked into it that makes what I'm trying to describe not be able to be seen properly. So we'll revisit that idea. Okay, so let's go back to the other picture. The idea is that I can think about having different planes come through and cut through this point, right? Each different direction that I choose, and assume that I'm restricting my directions to those that are vertical planes, but the angle of the plane can change. All right, hold on. I get to fight my computer again. I know. I don't understand. It's... Let me see if I can gather my thoughts here, and then I'll put the screen back on when things are going. All right, so the idea is that we have a point that we have selected on our surface. And we have a vertical cutting plane that goes through that point. And the picture that I want you to try to see in your mind's eye is us rotating that plane about the point on the vertical axis. And at some rotation of this plane, if we think about all of the tangent lines that we get we take the intersection of that vertical plane with the surface, that creates a curve, and then we look at the slopes of the tangent line at the point for that thing on its rotation all the way around. There should be, in theory, some maximal slope, right? There's a tangent line that's going to have the largest absolute value, and we would like to find, if possible, that maximal slope. Okay, so when we talk about maximizing the directional derivative, that is the picture that we're supposed to be imagining. And so what we want to do is figure out in what direction does the maximal directional derivative point. And we'll have to cut the foreplay, I guess, because of what happened with the projector. And the answer to this question turns out to be the maximal directional derivative is the gradient. Okay? So they're encoded in this gradient quantity that we're already familiar with. It is going to be what we refer to as the direction of steepest descent. Okay? So we compute the gradient at the point, and the steepest descent line or the steepest descent direction is going to be that gradient value. Okay? Now, of course, we have to be careful when we're writing down our formulas for everything in order to make sure that when we use our directional derivative formula that we use a unit vector in the direction of the gradient in order to compute the directional derivative properly, right? Because this formula here requires that this be a unit vector, okay? So we have to make sure that we make that adjustment in order to get everything in line, but the thing that is very, very important for this idea is the way that it relates to applications, okay? Number one, we have a quantity that we already want to be computing for the purposes of having an easy to utilize directional derivative formula, okay? Now, if we're talking about computing the directional derivative in the gradient direction, which this would be a way to write this, right? Of course, you would need this as a unit vector. But what it gives you is the gradient dotted with itself divided by the magnitude of the gradient, right? That's the formula at the top of the screen in the direction of steepest descent, dividing by the necessary factor in order to make the second gradient f a unit vector. Okay, so we have that easy way to write things down, which is super nice. Okay, and then what we will do for application problems is in the example that I brought up last week before the weekend, talking about the kind of the big problem of maximizing or training a neural network where you have many, many inputs and many, many independent variables, okay? The gradient doesn't care how many independent variables you have, right? So what you do is you compute the derivative with respect to each of those values, and you can get the direction of steepest ascent, or put a minus sign in front of it and get the direction of steepest descent, and then try to imagine your surface as something that tells you how much error is in the system, and you try to traverse to the part of that surface that is the shortest, the lowest altitude. But if altitude means error, the lowest altitude means minimal error. And so you can think about this as a very, very high dimensional calculus problem, okay? Which sounds bad, but all of the functions that you're working with, look like this. They're all lines. Okay, so taking the derivatives is super easy, but you plug this into the next function up. Okay, all my stuff's crashing right now. Anyway, but that's how it all builds out. Okay, so what you will see as you progress in your studies is these ideas that for us right now we're talking about the basics of are just scaled up to deal with more sophisticated problems. The math doesn't get more challenging. There's just more information to keep track of. All right? So keep that in mind, and don't be daunted by some of these projects that you see happen in the real world. It's just what you know how to do, except you have to do it hundreds of times. Okay? And make sure that you understand well enough what's going on in order to get the sequence of those operations correct. So enjoy your day. Sorry about the tech problems, and then hopefully we can get those sorted out here without too much more trouble. Yep, take care.